Okay. Today let us see the orthonormality of computational basis. What are computational bases? Computational basis. What form the computational basis in quantum? If you ask me, if I ask you also, you will be telling ket0 and ket1 form the computational basis. What is ket0? Ket0 is 1, 0, guys. And ket1 is 0, 1, as you know. Okay. Now, how do I find orthonormality? What's the definition for orthonormality? Orthonormality definition goes like, suppose if I have a state or a ket, okay, orthonormality definition goes like, the inner product of ket xi should be 1. Okay. With itself should be 1. Suppose if I have two states ket xi and ket phi, then the inner product of ket xi with itself and the inner product of ket phi with itself should be 1. Also, the inner product of ket xi with ket phi should be 0. That means what? Orthonormality is in between same kets, the inner product should be 1. In between the inner product between two kets, it should be 0. Now coming to computational basis. Now what I already have ket 0. What would be its dual? Bra 0 would be just the transpose of ket 0, guys. So what do I get? The column vector becomes a row vector. Now coming to ket 1, if I want the dual of ket 1, what will be the dual of ket 1 is transpose of ket 1. Bra 1 would be 0, 1, the row vector. Okay. Yeah. Now just see the orthonormality. 0, 0 would be something like 1, 0 and 1, 0. The row 1, 0 and the column 1, 0. Okay. Similarly here, inner product of this would be 0, 1, 0, 1. Okay, just go with the matrix multiplication. 1 into 0 plus 0 into 0 would give me 1. Here also 0 into 0 plus 1 into 1 would be 1. Okay, hence um, also I will check this. I will check the inner product between 0 and 1 or 1 and 0. Both of them you can check. Either one you can check. 0 and 1 would be, what would it be is 1, 0 and column vector 0, 1. So what do I get? I get it to be 1 into 0 is 0, 0 into 1 is 0. Hence it is 0. Hence, what can I say looking at the definition of orthonormality is ket 0 and ket 1 form orthonormal basis. Orthonormal basis is what I can say. This is how I will prove the orthonormality of the computational basis. Okay. Yeah, this is one question. Another question would be on finding eigenvalues and eigenvectors, guys. Find eigenvalues and eigenvectors, okay, of pi by 8 gate. What's this pi by 8 gate is, it's been given as pi by 8 gate denoted by t. This is equal to 1, 0, 0 ei pi by 4. Okay, guys? Yeah. Now you see here, it's very easy. How do I find eigenvalues? I first consider the characteristic equation. Characteristic equation. What's characteristic equation? Det t minus lambda I is equal to 0. Okay. Yeah. Lambda is my eigenvalue. Lambda is eigenvalue. First I consider characteristic equation. Then I go with the remaining things. Now, what would be the characteristic? How does the characteristic equation look like? Is something like 1 minus lambda 0, 0 e power I pi by 4 minus lambda is equal to 0. Now, clearly I can see, guys, it's a diagonal matrix. Now from the properties of eigenvalues and eigenvectors, eigenvalues of a diagonal matrix, eigenvalues of a triangular matrix, upper triangular or lower triangular matrix, the eigenvalues are just the diagonal elements. Eigenvalues of a diagonal matrix are the diagonal elements. What are the diagonal elements? 1 and e power I pi by 4. Okay, let this be lambda 1, guys. Let this be lambda 2. How do I find eigenvectors? Let's check. Let ket xi be the eigenvector. Okay, let me define how ket xi look like. Ket xi is equal to alpha 1 and alpha 2 be the eigenvector of t. Then how does it look like? Just see, what I need to consider is t ket xi. This is equal to lambda 1 ket xi. Okay, let it be xi 1, guys. Hence, I am considering lambda 1. Okay, yeah. Now, what is t? 100 e power I pi by 4. Ket xi is alpha 1, alpha 2. This is equal to lambda 1 is 1, guys. So it would be right side also would be alpha 1 and alpha 2. Yeah. Now what happens? Alpha 1 is equal to alpha 2 is what I get from the first equation. From the second equation, e power I pi by 4 alpha 2, this is equal to alpha 2. Now just see here, what will I get from this? What will I get from this is uh, alpha 1 minus alpha 1 is equal to 0. Okay, fine. Right, now from this you see, I cancel out alpha 2 on both sides. E power I pi by 4 is equal to 1. What is e power I pi by 4? The De Moivre theorem or cis is cos pi by 4 plus I sin pi by 4 is equal to 1. Can this be equal, guys? Can this be equal? It is equal. See, cos pi by 4 is 1 by root 2 plus I by root 2. Okay. A complex number can never be equal to a real number. Hence, what should I say here clearly is alpha 2, this is possible. LHS would be equal to RHS only if alpha 2 is equal to 0. So, I can clearly see that in ket xi, alpha 2 is 0. Okay. Nothing about alpha 1 is derived. Okay. So, I will take randomly, let alpha 1 is equal to some k. So, this would be k. That would be my eigenvector for lambda 1 is equal to 1. Yeah. Okay. Now, for lambda 2 is equal to e power I pi by 4, let ket xi 2 be the eigenvector, guys. I'll consider like this. Then what happens? T ket xi 2, this is equal to e power I pi by 4 xi 2. Ket xi 2. Okay. Yeah. So, 100 e power I pi by 4 alpha 1 alpha 2 only. Get xi 2 also looks something like that only. E power I pi by 4 alpha 1 alpha 2. Okay. Let's simplify LHS and RHS. Alpha 1 is equal to e power I pi by 4 alpha 1. Again, this is possible only for alpha 1 is equal to 0. Because again, it results in the same case where a complex number is equal to a real number. Okay, guys? Yeah. Now you see, for coming to the second thing, e power I pi by 4 alpha 2, this is equal to e power I pi by 4 alpha 2. Okay. So I cancel out e power I pi by 4. Alpha 2 is equal to alpha 2. So what I'll choose is let alpha 2 is equal to some K2. Okay, so ket xi2 would be something like 0 K2. Okay. Now what are the eigenvalues for lambda 1 is equal to 1? Eigenvector ket xi1 is equal to 10 K1. And for lambda 2 is equal to e power I pi by 4, ket xi2 is equal to 0, 1, K2. Okay. These two are the, of course, What I have got is this is my ket 0 guys and this is my ket 1. The eigenvectors for the pi by 8 gate are just the computational basis. Okay. This is one problem. Another problem that we'll talk about is another problem. Let me look at the another problem. Let me tell you about another problem. Okay. Next one would be suppose if I have ket xi is equal to 1 by root 5 ket alpha minus I root 7 by 15 ket beta plus 1 by root 3 ket gamma. Okay. What is being given to you as a small information, that is ket alpha, ket beta and ket gamma are orthonormal. They form orthonormal bases. That means what? I'm sorry. They form orthonormal bases. That means what? As defined earlier in the first problem, what happens is uh, inner product of alpha with alpha, of course, beta with beta, and gamma with gamma is 1. Of course, all the other combinations are all zeros, guys. Okay, you can just imagine all the other combinations. Anyways, I will write. What the question is, let me finish it off. Evaluate the inner product of ket xi is the question. Evaluate inner product of ket xi. What is ket xi? Let's see. I mean, inner product of ket xi. How do I write it? Inner product of ket xi is nothing but this one. Okay. You are being asked to evaluate this. Of course, let me finish off the remaining ones. Inner product of beta with gamma and inner product of alpha with gamma are all zeros, guys. Okay. Yeah. Now for the inner product, I have ket xi, guys. I want its dual. Okay. What do I need? It's dual Brazai. Okay, so how do I find the dual when I'm given things like this? See here, 1 by root 5, no change if it is a real number, guys. Okay, if there is an imaginary or a complex number, minus I becomes plus I. Dual is nothing but complex conjugate, guys. Complex conjugate. Okay. Yeah, for the ket also, it is its dual. Right? So for ket beta, it is bra beta. Right? Again, 1 by root 3 is a real number, so no issues. Right? So what I'll have would be the dual of gamma. I'm sorry, not xi. The dual of gamma. Writing the notation is the difficult task. Remaining things I think are not that complicated. Math is enjoyable in complex, in quantum. Okay. Yeah, let me do the net product now. One, just see here, guys. I can clearly see. Please see here. Again, what happens here is 1 by root 5 whole squared is what I'll get. And also what I'll be getting is alpha, okay, inner product. Next, I into I is minus 1, plus into minus is minus, hence it becomes plus root 7 by 15 whole squared is what I will get. Inner product of beta, okay, plus 1 by root 3 whole squared. Now clearly I can see since alpha, beta and gamma form an orthonormal basis, 1 by 5 into 1 plus 7 by 15 into 1 plus 1 by 3 into 1. Okay. Now once I finish taking LCM for it, 3 plus 7 plus 5 by 15, this is equal to 1. Yes, yeah. Can I tell that Ketzai forms an orthonormal basis? Okay. Yes, because inner product is 1. Ketzai forms orthonormal basis. Orthonormal basis. Okay. Yeah. This is one example. Of course, along with this, what else I have are, you can also check this question. Another question I can discuss. That is, what that is I think this is the fifth one, I suppose. Okay. Yeah. You are being given a density matrix, guys. Rho is a density matrix with 2 by 5 minus I by 8, I by 8 and 3 by 5. Okay. You are asked to test whether rho is Hermitian. Hermitian unitary. Okay. What's Hermitian? You know, it's a very basic thing for matrices. What is Hermitian, guys? Hermitian is similar to your symmetric matrix. Symmetric matrix. What's the symmetric matrix? I know if A is equal to A transpose, matrix is symmetric. Okay. Then what is Hermitian matrix? Hermitian matrix is discussed for complex matrices, guys. If there are complex or imaginary numbers, complex or imaginary numbers in the matrix, then I talk about it as Hermitian, because complex numbers always occur in conjugates, guys. If you have to understand what exactly I'm talking, see, if I have this expression, guys, x squared plus 1 is equal to 0, what would be the roots of it is x squared is equal to minus 1, x is equal to plus or minus I. Okay. Whenever there is a plus I, there is a minus I. Whenever there is a minus I, there is a plus I. Never the complex numbers occur in single. They occur only in conjugates. So, instead of directly transposing the matrix, for the matrix with complex numbers, I find the conjugate and then transpose it. Okay. Or in other words, what exactly I need to check for is, for Hermitian, what I need to check is, for Hermitian property, I need to check rho into rho theta. No, I'm sorry. Just a second. Rho is equal to rho theta or not is what I need to check. What is rho theta? Rho theta is nothing but your conjugate transpose, guys. Just a second. Conjugate I denote by bar, transpose I denote by t in the power. Okay. So what's the conjugate of rho? Let us check. What's the conjugate of rho, guys? Rho is this matrix, guys. By the way, density matrix. Okay. There is no conjugate for real numbers. Conjugate is itself. No conjugate, I shouldn't say. I'm sorry. For a real number, the conjugate is itself. For a complex number, conjugate is nothing but x plus iy. If I have, its conjugate is nothing but x minus iy, guys. That's it. Okay. Yeah. So, minus I by 8 becomes I by 8. Okay. Next, minus I by 8. Okay. For a real number, the conjugate is itself only. Next, what I need to do to find rho theta? I'll just change the color. Yeah. For rho theta, what do I do is conjugate transpose is what I will do. So what I will do? 2 by 5 minus I by 8. I by 8. 3 by 5. Check with rho, guys. Is it the same one? Yes, it is the same one. Hence, I can say that rho is Hermitian. The given density matrix is Hermitian. Now, coming to unitary. How do I check whether a matrix is unitary or not? Let me show that to you. How do I check a matrix is Hermitian, unitary or not? Unitary, again relating to your real matrices. When do I call a matrix to be unitary is, or unitary is similar to your normal matrix. What's a normal matrix? A into A transpose is equal to I. Okay. So let's see whether it's unitary or orthogonal, by the way. Orthogonal also I can say A into A transpose is equal to I. Now coming to unitary, what I need to check is Rho into rho theta is equal to I is what I need to check. I already have rho and rho theta, both are same. Let me check. Okay. 2 by 5 minus I by 8, I by 8, 3 by 5 into 2 by 5 minus I by 8, I by 8, 3 by 5. Okay. Does it come to 1001 is what I check for. If it comes, then it is unitary, otherwise it is not. Okay, 2 2's 4 by 25. Okay, next is what? A11 into B11, A12 into B21. Okay, so what I'll have? I into I minus minus into minus becomes plus 1 by 64. Okay, next one. Yeah, 2 into minus 1 by 8. So minus 2I by 8 5 is 40. Plus again it becomes minus 1 by 64. 1 only, na? No, 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 no. 2 into this and minus I into 3, 3, 3. Okay? Yeah, this would be. Okay, this would be minus 3I by 40, guys. I'm sorry. Okay. Yeah. 2I by 8 5 is 40 plus 3I by 40 again. Okay, next. I into I is minus minus into minus is plus 1 by 8 8 is 64. And then plus 9 by 25. Anyways, I can clearly see it doesn't turn out to be 1001. Hence, rho is not unitary. Unitary, it is Hermitian, but it is not unitary. That's what I will write. Okay, that's how I will check for the matrix becoming Hermitian or unitary. Okay, yeah. There's one more question which I will do. Okay, yeah. Uh, Yeah. The thing is, estimate the projection operators. Projection operators. The question is projection operators formed by the computational basis. Again, in the first question, I said formed by computational basis. What are computational basis? Your ket 0 and ket 1, guys. Okay, computational basis. The projection operator formed by computation excuse me, formed by computational basis. What are, excuse me, yeah, what are your computational basis? Ket 0, ket 0 and ket 1 are your computational basis. Yeah, how do I define how do I define projection operator? Just a second. Little water. What are your computational basis? Ket 0 and ket 1, guys. What are projection operators? See, guys, how projection operator is defined as projection operator usually is denoted by Pn. Okay. How is it defined as? Uh, of course, see here, P0. How P0 is defined as ket 0, the inner product of ket 0. Okay. No, no, just a second. It is, I think, the outer product and not the inner product. Let me erase this off also. You are also asked to check the completeness relation, guys. You are asked to check the. Okay. How do I define a projection operator? Please see here. Once I finish defining, things are very easy. Definition of a projection operator denoted by P, guys. For a state ket xi, for a state ket xi, how do I define P is, it is the outer product. Outer product. Okay, how is it? Just see here. Ket xi. This is how I define outer product. You know inner product, the ulta way of writing is outer product. Okay. Now, for the computational basis, I will denote this by P0. How do I define the outer product? Ket 0 and its dual. Of course, the outer product is defined P1, the outer product of ket 1 and its dual. Okay. Of course, I know in the previous examples I have written what is ket 0 and what is its dual. Okay. Ket 0 is nothing but your 1 0, the column vector, and its dual is nothing but the row vector. Okay. For this, similarly, the column vector 0 1 and this one 0 1, the row vector. Okay. Just start multiplying. See what happens. By the way, guys, inner product always results in a number. Outer product results in a matrix. Okay, remember that. 1 into 1 is 1. 1 into 0 is 0. 0 into 1 is 0. 0 into 0 is 0. A matrix. P naught is a matrix. Now coming to P1. 1 into 0. Of course, just check whether they are compatible or not for multiplication, guys. 2 into 1. 2 rows and 1 column. Here I have 1 row and 2 columns, right? So finally I'll be getting a 2 by 2 matrix. So compatible for multiplication. Okay. 0 into 0, 0 into 1. 1 into 0, 1 in 0 into 0, 0 into 1 is also 0, guys. 1 into 0, 1 into 1 is 1. This is nothing but your P1, guys. Okay. Now I've got this. Now there's something called verify completeness relation. Verify completeness relation. Okay. What is completeness relation? Just see. Completeness relation is nothing but sum of all PIs should give me an identity matrix. Again, I repeat, guys. The projection operator in quantum is defined as the outer product of the states or kets. Okay, if I have ket xi, it's the outer product of ket xi with itself is defined as the projection operator P. Now, for ket 0 and ket 1, I am denoting by P0 and P suffix 1. Now, how do I verify completeness relation for this computational basis is, I sum up all the projections and it should turn out to be I, the identity matrix. Let's see what happens, guys. Let's see what happens. It is nothing but P naught plus P1, guys. It is 1 0 0 0 and 0 0 0 1. Okay, this results in one addition. You all know matrix addition, right? It results in an identity matrix. Hence, completeness relation verified. Hence, completeness relation verified. Okay, this is how I will write. This is one example again you need to check for. Also, there's one more different one. I don't know how many of you remember. This one example. How many of you remember? I don't know. Let me write it down for you to recollect. Yeah. That is uh, seventh one, I suppose. Evaluate. You need to evaluate tensor product of x and y with ket xi. Okay, what is ket xi? Let me write how ket xi is defined. Let me write 0, 1 minus 1, 0 by root 2. This is how ket xi is defined, guys. Tensor product you are asked to find. What do you think are capital X and capital Y, guys? Capital X and capital Y are your Pauli gates. Pauli X and Y, Pauli X and Pauli Y gates. Okay. And you ought to know to evaluate this, you ought to know the matrices, guys, for Pauli X and Pauli Y. Okay. Capital X is nothing but your 0 1 1 0. The flip you will say, na? The flip gate is what you will say, right? Yeah. Next one is your Y gate is nothing but 0i minus I and 0. Okay? Yeah. Now, how do I do it? Just see, guys. This is very important. Why, you know? Whenever I'm calculating tensor product of operators, tensor product of kets is easy, guys. Tensor product of operators is a bit typical. Okay, tensor product of operators is a bit typical. You ought to know about it. Of course, once you know the small logic, you will do easily. Okay, what it is, just see. Suppose if I have operators x and y, of course, guys, please see here. I think many of you know this is again a shorthand notation for the tensor product between ket0 and ket1, guys. Okay, all of you know, those who are aware of tensor product, the shorthand notation, always writing that multiplication symbol, the cross symbol in a circle is every time writing is difficult. So shorthand notation is ket 0, ket 1. It's nothing but the tensor product. Now you see, I have tensor product on operators capital X and capital Y, guys. This has to be operated on two states, ket 0 and ket 1, guys. How do I do it? If you understand this logic, the whole problem is damn easy, dead easy and damn easy. See what's the logic is. When I am doing with operators, the first one operates on the first one, second one operates on the second one. That is it. And then you ought to know about what happens if x is operated on ket 0, what happens if x is operated on ket 1. You ought to know. If you remember, it's fine. If you don't remember, you'll operate and see. It's not a big deal. Obviously, they are just one matrix and a column vectors. You can operate on them. You can multiply and get the value, which is not a big deal. Okay. But what is a big deal? What's the important thing is when operators are being operated on states or kits. See, two operators, there should be two states. Okay, why? Because one first operator on the first state, second operator operates on the second state. If there are three operators, then there should be three states. Okay, the logic is like that. Now once you understand the logic, you can do it very easily, this job. Okay, what's been asked? X tensor product of y with ket xi has been asked. Okay. Now, what's it? X tensor product of y. What's there? Let's see. What's been given as ket xi is 0, 1, 1, 0. Okay. So, this I will write like this. 0 tensor product of 1. Okay. Minus x tensor product of y ket 1 tensor product of ket 0. Okay, that shorthand notation you expand and write now so that your things are clear and I clearly apply the property. Okay, yeah. Now what happens? Very simple. X on ket 0 and it's just a normal multiplication, guys. Y on ket 1. Okay, minus x on ket 1 and y on ket 0. Okay, I'll just give you a minute time, 1 minute time. Just see it if you can guess the answers. You can get them easily or not. Do check, guys. Are you able to apply and get the answers easily, or do we have a problem in getting those? In the meantime, I'm just searching for another problem. Okay, I'm searching for another problem. You just think whether things are understood or not to you. Okay, you got it? You understood what's happening? Okay, let us proceed with the answer. Let us proceed with uh, what happens when the operators x is applied on ket 0 and okay, what happens when x is applied on ket 0? What happens when x is applied on um, Ket 1, that decides my answers. That's it. Okay. That decides what answers I'll be getting. Okay. Yeah. Hmm. So X on Ket 0, what happens is it flips Ket 0 to Ket 1, guys. That's it. Okay. Yeah. What happens? X on Ket 0 flips Ket 0 to Ket 1, guys. Okay. X on Ket 1 flips Ket 1 to Ket 0. Okay. Similarly, when I apply Y, of course, there's a shift in phase, a shift in both. I mean, phase flip is there, and also your bit flip is also there. Okay. Yeah. Let's see how we can write. Of course, we can put it in tensor product only, or otherwise we can go with Ket 0, Ket 1. Okay. Yeah. So I can write this as a Ket 1, guys. Okay. When Y applied on this, I just need to look. When Y applied on it, uh, what's the flip that is there? I can check, of course. Just a second. What's Y? I have given Y here, na? 0I minus I 0. Okay. Yeah. So 0I minus I 0 when it is applied on 1 0. What do I get? See, 0 0 1 0. Okay, 0 0 1. No, no, I 0. So I into Ket 0 is what I'll get. Why when applied? 0 minus I 0. When it is applied on 0 1, what happens? 0 minus I. Okay, 0 0. Okay, so once I know the answer, I'm done. Yeah, this is one. I see here. This is one. This would be what? Uh, I into Ket 0, guys. Minus, of course, tensor product again. Of course, if I write them together also, it represents. See here, what I mean to say here is, of course, I wasted a bit of time in searching if I can get some other question. Okay. This is 0 and this is, no, no, bit flip. So this is 1, guys. 1 and I get 0. If I write also fine. This is tensor product. Understood obviously, right? Now coming to, it should be minus I get 0. What's this? Something I messed up. Just a second. 0 and 0. Okay. I and 0. Okay. So this is get 1. This is face flip and bit flip. Face flip because there's a change in sign. Okay. Yeah, now this is minus I into Ket 0, guys. This is I into Ket 1. This is I into Ket 1 minus, this is Ket 0 minus I into Ket 0 by root 2. Okay, I'll take I common first. Okay, what I have is Ket 1 tensor product. I'll write here clearly. Ket 1 minus Ket 0, Ket 0. Guys, minus into minus here it becomes plus under root. Okay. Yeah, you may leave it like this. Otherwise also I can tell you how to write the answer. Okay. I by root 2, leave it out. Now Ket 1 is 0 1, guys. Tensor product of 0 1. Okay. Minus 1 0 tensor product 1 0. Okay. Once I am done with this, see what happens. I by root 2, of course, I don't think it fits here. I'll write in the next line. I by root 2, okay. Yeah, 0 into anything is 0 only, guys. 0, 0 is what I'll get. 1 into 0, 0. 1 into 1 is 1. The last element, guys. Here, 1 into anything is the anything only. 0 into anything is 0 only. So finally, what would be my answer? Just see, very simple. 1 minus 0 minus 1, 0 minus 0, 0 minus 0, 1 minus 0. So what I'll get would be I by root 2, guys. This is minus 1, 0, 0 and 1 is my output. This is how I will evaluate and get the answer when the tensor product is between operators and states. Okay. Yeah. I think I'll end this video because this has become lengthy. I'll make one more. Okay.